All right, this begins lecture 4, part 2. This is the second video on this chapter. In this chapter, we'll cover primarily one thing, which is basically the Lewis model of acids and bases. So remember in the previous video, we covered the Arrhenius model as well as the Bronsted Lowry model. The Lewis model is the most recent model, the most modern model, and incorporates the most compounds that can be classified as acids and bases. So the Lewis model is named after Gilbert N. Lewis. This is the same guy who put forth the idea of Lewis dot structures. This is actually a picture of Lewis, Gilbert Lewis. He was actually nominated for the Nobel Prize in Chemistry 41 times, but actually never won it. There were some political things that were going on, and so he actually probably deserved the Nobel Prize, but never ended up winning it. He did come to a kind of sad end. He worked for many, many years as a professor at UC Berkeley, and he actually died from hydrogen cyanide poisoning in his lab towards the end of his life. So anyway, you can read a little bit more about him yourself, but this is the same guy who developed the Lewis dot structure model that also developed this Lewis model. Okay, so under this model called the Lewis model, okay, a Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. Okay, careful here, they don't say H+. H+ was in the Bronsted Lowry model. Here they're talking about electron pairs. Okay, so let's look at an example. Okay, you have NH3, and we've drawn it as the all the bonds and lone pairs as electron pairs. And so really, when the NH3 reacts with H+, what happens is this lone pair of electrons actually does something what we call, it forms a bond. And we saw a little bit of this in the previous video between the nitrogen and the H+, right? So this is really the new covalent bond that is formed here, right? This is your new covalent bond. Okay, so if you're looking at this model, okay, who is donating the electrons? The electrons being donated to form this bond is actually on the NH3. So because of that, it is called the electron pair donor, and therefore it is the base. Okay, now H+ actually accepts a pair of electrons to form this new covalent bond, so it is an electron pair acceptor, and so we call it an acid. Okay, and if you want, you can pause the video. It's very important to write this down in terms of the acid and base. The acid is the electron pair acceptor, and the base is the electron pair donor. Okay. So in this model, very important to note, you don't need to have an H anywhere. Okay, and I've basically rewritten the definitions that we had in the previous slide just so that we can refer to it. Okay, let's look at these two examples here. You have O2 minus, okay, and it so these electrons are forming a bond. Okay, again, this pink arrow is forming a bond. Okay, and it is this new bond that is being formed right here. Okay, it is true that these two electrons actually do move out onto the oxygen, and this becomes a lone pair. Okay, but notice what is happening in the formation of that one bond between oxygen and sulfur, right? Oxygen is actually donating electron pairs, right? These two electrons are being donated to form a bond. Okay, and really sulfur is accepting electrons to form this bond, right? So based on our definition, okay, the oxygen is donating, so it is the base, and the sulfur is accepting the electron, so it is the acid. Okay, again, let's look at another example here. You have your NH3, and again, it's got a lone pair. It is going to form a bond to the boron, okay, and so this is the new bond that is formed here. Okay, so in this particular case, again, the nitrogen is donating electrons to form this bond, and the boron, which is electron poor, doesn't even have an octet, okay, is accepting electrons, and so it is the acid, okay, because it is accepting electrons. So, in fact, a lot of molecules are formed this way. Let's look at an example of aluminum reacting with 6 waters. Okay, each one of the waters will donate an electron pair to form a bond to aluminum, and it'll form six bonds, right? 6 waters forms 6 bonds. Okay, and we call this Al, and a lot of times people will write it like this: Al parentheses H2O, and then 6, and it carries a charge of 3+. And with these kinds of situations, it's very important to remember that if you treat the arrow as an equal sign, okay, the charges do add up. So if you have 3+, and water is, remember, neutral, 3+ plus neutral should give you 3+, okay? The reason that aluminum can be a Lewis acid, remember Lewis acids like to be either electron poor, okay, or it doesn't have an octet. Okay. Aluminum has unoccupied 3s and 3p orbitals, right? So you can actually put electrons into the 3s and 3p because it's empty. So aluminum 3+ makes an excellent Lewis acid, okay? So again, under the Lewis model, the acid is usually positively charged. So in this case, aluminum is positively charged, or electron poor, or both, okay? Or it doesn't have an octet. Electron poor meaning it doesn't have an octet, okay? So let's try and identify some Lewis acids and Lewis bases using this model. And again, you can represent the bond that is formed as a line to make it easier to draw, okay? So it says, in the following reactions, identify the Lewis acid and the Lewis base. And you should write equations using Lewis electron dot formula like we've been doing in the previous examples to identify who is donating and who is accepting. All right, so let's go ahead and draw the first one. So we're going to draw Ag, and it's plus, okay? And you've got 2 NH3, so I'm going to draw one on each side. I'm going to draw an NH3 on this side. Okay, remember NH3 has a full octet, so it has a lone pair. And this is another NH3. And again, a lone pair, okay? What is happening is that this lone pair will form a bond to silver. This lone pair will form a bond to this silver, okay? And what will happen is you'll have a bond being formed, another bond being formed, okay? And really in the center is your Ag, and you've got your 2 nitrogens here. And of course, on each nitrogen are 3 hydrogens, okay? If you're looking at what we've drawn here, who is donating electrons are these 2 NH3s, right? They're donating electrons, right? So we're going to call these the base. Okay? And the Ag, or the silver plus, is accepting electrons, so it is the Lewis acid. Okay? And last but not least, remember to keep track of the overall charge. You've got a neutral NH3, a neutral NH3, and a positive silver, so you should have a positive species there. Okay, let's do another example. You've got your boron with your 3 OHs. Okay, and notice boron is electron poor. It does not have an octet, so it's a very good clue that it's the acid. Okay, and then you've got your water, and I'm going to draw water suggestively like this. Okay. And in fact, what I'm going to do is I'm going to draw this bond in red so that you can see what is happening. Okay, so this pair, remember this is an electron pair, this is 2 electrons. It will actually form a bond to the boron, leaving behind an H+. Okay, so what happens is there's a new bond that is formed. Okay, on one side of it is your boron. On the other side of it is your oxygen, H. And this oxygen has 2 lone pairs, okay? What is left over is your H+ hanging out here, Okay. Okay. A lot of times we'll just write it here just to, you know, it's not connected to each other. And of course on the boron is your 3 OHs. Okay. And remember, you have to keep track of the charge in terms of the H+. This must be negative because you have neutral and you have, this is neutral and this is neutral in terms of your starting material. Okay, so you've got to have neutral on the left as right as well. So minus and plus will give you a neutral species. Okay, so again, who is donating electrons? Where's the arrow originating from? It's the water, right? The water is the donating of the electron. So this is your base. Okay, and your boron is your acid. And it's very easy to know that because remember, the boron is electron poor. So it is always your acid because your electron poor or your positively charged species. Here your silver is positively charged. Okay, so it must be your acid. Okay. Let's look at one more example, and you will have to draw these on your homework, so it might be good to take notes as you're following along in terms of this video. Okay, so we're going to do BF3, and BF3 is again boron with 3 Fs on it, or 3 fluorines on it. Okay, and again it is electron poor, it does not have an octet. Again, most likely this is going to be your acid. That's a big giveaway. Okay, and then you have your methanol, so you have your CH3OH. So I'm going to again draw it suggestively. Oh, I can't say today. Okay. Okay, I'm going to draw it so it makes it easier for you to see where the bond is being formed. Okay, because these lone pairs is going to form a bond with this boron. Okay, and so what does it form? It forms a new bond. Okay, and on one side of that bond is your boron. And on one side is your oxygen, okay? And its oxygen is still got the lone pair, it's still got the hydrogen, still got the CH3, okay? And on the boron, of course, you have your 3 fluorines, okay? And because this is neutral and this is neutral in terms of the starting material, your product is, of course, going to be neutral, okay? And a lot of times we just indicate the charge with a little kind of bracket here and then the charge up like this, okay? So because, again, these electrons are being donated on the OCH3, then this is your electron donor. And an electron donor is always the base. And this is your electron acceptor. And therefore, it is your acid. And again, because it's electron poor, it was very obvious from the beginning. Okay. Last but not least, you have B. B is O2 minus. Now remember, oxygen neutral is 6 valence electrons, okay? But O2 minus means it has gained 2 more electrons, so we say O2 minus. Those are the 2 electrons being gained in red, okay? And it reacts with CO2, and again, CO2 is carbon dioxide. Hopefully you remember from 151 that carbon dioxide is linear and has 2 double bonds, okay? And so what will happen to form CO3 2 minus is that this electron pair here will form a bond with the carbon. Okay. Now, carbon cannot be hypervalent. It cannot have 5 bonds attached to it. So you need to move some electrons up, and that's exactly what we're going to do. We're going to move some up onto this oxygen. Okay. So let's draw the result of this movement of electrons. There's a new bond that's formed, and that bond is between the oxygen and the carbon. Okay, and I'm just going to draw the leftover lone pairs still hanging out. Okay, on the carbon here, there is still an oxygen that's double bonded. Okay, but this oxygen is no longer double bonded; it is single bonded. Okay, and these electrons that were this bond here is moved up to become these electrons. Okay, so notice in this particular case, everything still has an octet. Okay, but it should have an overall charge of 2 minus. Why? Because the oxygen was 2 minus, the carbon dioxide was neutral, so 2 minus plus 0 should still give you 2 minus. This is another way to draw carbonate or CO3 2 minus. Okay, so you will have to draw these in the homework, and on the exams you will have to identify either what is the acid, what is the base, what is the electron donor or the electron acceptor. Another kind of question you will get asked on a quiz or an exam is to identify which of the arrows that I've drawn is correct and which of the arrows I've drawn is incorrect. Remember, your arrow should always start. This is very important to remember. Your arrow needs to start from electrons or electron pairs. Okay, so you either need to do this. Oftentimes I will circle them to show you that these are the ones that are moving, or if you have a bond, those are electron pairs that are moving. But it always needs to start from an electron pair and end on an electron pore atom. So your arrow should end on an electron pore atom. Okay, either something that doesn't have a full octet or something that is positively charged. Okay, so your arrow should either end at something that is electron poor, like boron, for example, okay, or something that is positively charged, either Al3 plus, silver plus, etc. All right. So as a recap of all the models that we've covered in the last video and in this video, your Arrhenius model produces H plus as an acid. It produces OH minus as a base. The Bronsted Lowry model donates H plus and accepts H plus. And the Lewis model, the acid accepts electrons and the base donates electrons. Okay. So another kind of exam question that you might encounter is something like this, where it says in the reaction below, you've got calcium 2 plus. Can it be classified as an Arrhenius acid, a Bronsted Lowry acid, and or a Lewis acid? Okay, so let's look. What is really happening here is the calcium is reacting with the S2 minus to produce calcium sulfide, right? And if you wanted to, you could draw the Lewis dot structure. You can write sulfur is normally 6 valence electrons, okay? And it has 2 minus, so it's gained 2 electrons, okay? And calcium is all by its lonesome. It's got no lone pairs, no electrons, okay? And again, it's 2 plus, so you can right away know that that's probably your acid, and indeed that is the case. There's a bond being formed between your sulfur and your calcium 2 plus, and it forms calcium sulfide, okay? And so you write Ca, the line, S with its 3 lone pairs, and this is the new bond that is formed between the calcium and the sulfur. So in this case, can the calcium be classified as a Lewis acid? Absolutely. It is a Lewis acid because it is accepting the lone pair of electrons from the sulfur. Okay. Can it be an Arrhenius acid? Okay, and if you need to, you can look back at the chart. Remember, the Arrhenius acid has to produce H plus or donate H plus, depending on if it's an Arrhenius or a Bronsted Lowry. In this case, okay, calcium is neither of those. Okay, it is not an Arrhenius acid because there's no H plus involved in this reaction. There's no hydrogen involved. Neither is it a Bronsted Lowry acid because, again, neither of this, there's no H plus, okay? But under this newer model, the calcium absolutely can be classified as a Lewis acid, okay? And again, this is a reaction that we saw in lab number 4, iron 3 plus reacting with thiocyanate to form iron thiocyanate 2 plus. And the question says, can the thiocyanate SCN minus be classified as an Arrhenius base, a Bronsted Lowry base, or a Lewis base, okay? In this particular case, these electrons, there are electrons on the sulfur that is being donated to the iron, okay? And so I'm going to just circle this and draw it this way, okay? Really, what is happening is this is the base, and it is donating electrons, okay? And so this absolutely is a Lewis base, okay? But it is not an Arrhenius base. It doesn't produce OH minus. There is no OH minus in this reaction. And it doesn't accept OH minus, or H plus, sorry. It doesn't accept H plus. So therefore, it is not a Bronsted Lowry base. Okay, so you have to be able to go through each one of these situations, okay, and ask yourself, is it an acid, Lewis acid, is it a Lewis base, etc. Okay, one of the most popular exam-like questions is NH3. okay? And it reacts with H+, and it forms NH4, right? So in this particular case, it is a base, right? It does accept H+, right? It accepts an H+ to form NH4. It actually does not produce OH-, okay? There is no oxygen anywhere, actually. And actually, it donates electrons, right? And we can redraw this as the lone pair on this nitrogen, and we say that it forms a bond to this H+, okay? So it actually donates electrons, so it is a Lewis base as well. So NH3 is a Bronsted Lowry base, is a Lewis base. It is not an Arrhenius base, okay? So again, I would review some of these questions and make sure you understand how to qualify if it's an acid or a base under each one of these models, in terms of understanding the differences and similarities between these three models, okay? So this ends this video, and again, the thought here is you would understand what the Lewis model is. You would be able to draw these kinds of Lewis dot structures and show the formation of a bond with an arrow, and show the electrons being donated and the electron being accepted. Remember, the electron must end on an atom. It shouldn't end anywhere but on the electron poor atom, okay? So that you can clearly show where the bond is being formed. That's basically the main exercises in this video and in this part of this chapter that we were covering in this video. All right, that's the end of this video, and go ahead and do the homework questions related to these, and then go ahead and watch the next video, video 3. All right, I'm going to stop the video here.